So, yesterday we finished the first bigger topic of our course, that's namely mathematical statements. And we have started with the second bigger topic, that's the sets, introduction into the set theory. Right. And I want to recapitulate what we did in the section on mathematical statements, because that you should internalize. We will need it extensively. I will only shortly go over the things we did already within the introduction to the set theory. Okay, we defined a set as a collection of clearly defined, distinct mathematical objects. We have discussed what a set actually is. We have discussed some notation. We have had some discussions about what mathematical objects are in context of sets. Then we introduced some notation for sets, right? And most importantly, we introduced the notation which describes elements of sets via a property given after a vertical line in the set parenthesis, right? And then we introduced the number sets, the most basic ones. And when we started to define most basic objects within the set theory, that is the empty set, a subset, and we defined equality of sets. And we also had our first proof, which wasn't really deserving of this name, but nonetheless, we had our first glory and our first proof. And next up, we define the operations in sets. That is, now we proceed with that. All right. Let's get started. And let me look at how I would like to structure enumeration of the sections, right? That's 2, introduction to the set theory. That's the chapter, and that's 2.1. Basics. It belongs to this, and that's 2.1 basics. That goes until here, and 2.2 operations on sets. As we said, there are different notations for sets. For most general sets, we will just use letters, like for mathematical statements, but from the context, it should be clear what is meant where. All right. 2.2.1. Union. Let, and this let is a typical mathematical introductory word. If we want to talk about some objects, I didn't use it above, but now I will use it. Let A be sets, or, well, of course, in proper English, that would be let A be sets, but in mathematical Greek notation, it's sometimes omitted. Then we define, and in other places I probably won't state that in such proper English. It's clear that we define something. We define union, define operation. Again, just like by statements, this takes two sets and gives us a new set. Read union of A and B. B via, and what set does it give us? Well, the union is just the set of all elements for which it is true that an element is in A or in B, and we mean it. So if here nothing is specified of what it is an element, as compared to here, for example, then it is a general mathematical object. It could be object of any kind first, and then we specify what objects we mean. And those are the objects for which the following statement is true. And when I just write the statement there, we have already seen that by statements, but we have not specified that exactly. But when I just write statement there as this statement is the condition, then of course I mean this statement must be true. So it is exactly all those objects for which this mathematical statement is true. And the truth of this statement, as we have learned, only depends on whether those individual statements are true, and more precisely what truth values those individual statements have, right? And of course I do not do that. I could do that, but you understand that I just connect those mathematical statements, x element of A, x element of B, for which we can of course clearly evaluate it is true or it is not true, because set is exactly what tells us for each mathematical object, is this object in me or is it not in me, right? And you already see here we increase the degree of abstraction. Here we already use those statements pretty naturally in the description of sets. And subsequently, I won't pay that much attention anymore to specifying the abstract structures involved in their interplay. At least in many places, I won't do it anymore because it has to become self-explanatory for you. You just have to see how it works, and there's no other way in mathematical education other than just to get used to it and to internalize how this language works. I can't explain each step of building the structure, but here, at least one time, I will explain it directly. We state this statement in the description of the set, and that means this element has to satisfy this statement. That is, this statement should be true, and has to satisfy means, well, this statement involves this element, and it involves this element, and we evaluate this statement, and this statement should be true. So, since the element is involved, we say if the statement is true, the element satisfies the statement. All right, and this is exactly all such elements for which this is true. And on the second layer of interpretation, that just means, on the first layer, if you recall, we just evaluate the truth values of that, and we evaluate the truth value of that based on the truth values of that. And the second layer of interpretation, of course, is just all elements which we take and for which we see, well, we check this element is in A, okay, this statement is true. Maybe it is not an A, then we check if it is in B. Well, if it is in B, the statement is true. And of course, that already includes that if it is in both, then already by checking if it is in A, we would have postulated that it is satisfying the truth of the statement, because that is how the OR works. So it is including OR, which means one of the options, and that is any of the options, or both at once. Right. and that is the union. And the customary drawing for that is also called Venn diagrams. This is the set A. That is all the points in the circle are supposed to be the elements of the set A. That is, all geometrical points of the plane in this circle are supposed to be elements of in the set A depicted graphically. B, another set, and then we take the union. But of course, this is the customary drawing. But of course, you understand that those sets need not have common elements. If they share points, of course, it is common elements, as you can figure, because we said the points of the plane depict elements in the sets, and the points in this circle depict all elements in A. The points in this circle depict all elements of B. And now there are some points that are in both circles, so that's elements in both A and B. But of course, the sets could be, that is called disjoint. They don't have common elements, and this is the depiction of A union B. And of course, there might be different, for example, when they share only one element, these circles touch each other. It is a particular case of that, but like geometrically, it looks a little bit different. We are not interested in that because those drawings, they just illustrate what is going on. They can help you in some cases, but we are interested in the abstract definition. Okay. Well, the next is intersection. So intersection of sets A and B. And as promised, I won't write this anymore extensively. We just define the intersection. And the intersection is operation that takes the sets and is defined. We call that it is defined. The set that it produces from those two sets is defined as all mathematical objects X which are in A and in B. Right. And here you can see that the empty set that we introduce is very practical. For example, we could have this situation, right? This belongs to the union, but just think we could have this situation, just two sets. We don't have common element. So this is false. This is false for all X. Right? For all mathematical objects, it is false. For those objects that are neither in the set, and for those objects that are at least in one of the sets, because they are certainly not in the other, if we follow this depiction. Definition. If A intersection B is empty set, and this is exactly the case when the sets don't have common elements, that is, no element satisfies this, and that is exactly a way to describe empty set, right? So that is X with the property that X oh, of course, that's the same. Okay, we don't do that. I wanted to describe empty set generally, but okay, let's do that nonetheless. Just for completeness sake, but you don't need to think about it. X satisfying a statement P of X, a statement just like here. So just imagine an abstract statement and P of X is wrong. So the description of the set is itself contradictory. That is, no X could satisfy that. Right? For example, that's very simple. It might look abstract, but it is very simple. X in the nature numbers, X smaller than 0 is of course the empty set. Not the set containing the empty set. It would be a different thing, because empty set is itself a mathematical object, so it can be contained in the set. And if I would have written a set containing empty set, it would be that. But the empty set itself, set with 0 elements. And if A and B are the empty set, then we get a special name. If A intersected with B is empty set, then we call A and B disjoint sets. And B disjoint. So if intersection is empty set, which is the same as no X satisfies this statement, just like here, no X satisfies this statement, then it is of course intuitionally logical to say that it is empty set, and also mathematically it's just stated that this is empty set, and we just will understand what sets are empty sets. It is not necessarily formally defined, at least in introductory courses. There's no need for that. It is defined in advanced set theory, so to speak. But we just see the connection just by logical thinking, so to speak. So it could be defined completely precisely what an empty set is, that is defined in terms of mathematical structures. But we don't do that. We just say that is a set for which all of its elements like satisfy a wrong statement because it creates a contradiction, or it is a set that does not contain any elements. That's the most simple thing. And if no X, if we have a description of a set where we have mathematical objects X with a statement that can't be satisfied, then no X, no mathematical object is contained in the set, and then it is description of empty set. Right. And if we have that there is just no X that is in both A and B, then it is empty set. And if that is true, then the intersection of such two sets that have no common elements, like here, is empty set, and we call the sets disjoint. Right. There was a lot of fuss about a little thing, but what I said is important at some particular moments. You don't have to think about it deeply, but you have to internalize the mechanics that go with it without necessarily thinking of it explicitly, but you have to internalize them, and that's why I'm mentioning them, so that at some points of your mathematical path you'll be reminded of that by yourself when you see, oh, here it works like that because of that, and so on. For especially attentive listeners, I should also mention, yes, this is a quite special way to define empty set, which is not quite same as here, because here I'm defining my set as X for which a statement P of X exists. That is, a statement P exists such that P of X is true. That is, a statement P exists which is satisfied by P of X, which is satisfied by X, and for which simultaneously P of X is wrong. Clearly, no mathematical object can satisfy this, that a statement exists that is satisfied by it and simultaneously is not satisfied by it. I could also say false wrong or false. I use that interchangeably sometimes, right? And this is a special way because this P of X, the existence of a statement, it is now especially for X. So it is all object X, or it is, at least that is what we are stating. It is all object X for which such statements exist, at least one of them, for a fixed X, such that it is satisfied by X and it is not satisfied by X. Of course, it is a contradiction to our primary definition of mathematical statements. Statement is either true or false, right? And here it is a much easier thing. Here we are just given one statement and we apply it to different X. So we just fix an X and we look at the statement. For example, X is 5, 5 is bigger than 0, doesn't work. 5 is smaller than 0, does not work. But here, the statement could really, this form of the statement itself could depend on X. So it is a very special way to state the same mathematical object, the object of set containing no mathematical objects, because no object can satisfy that, and also no object can satisfy that. It is not that important to understand it precisely. It was just a pedantic note so that you understand that it is actually not quite an example of this. Only an example in the sense that this is both empty set, but yeah, generally this discussion just serves to give you a view of how it is possible to think of things and where intuition or intuitive definitions and mathematical formalization kind of collide and kind of are intertwined. Because if you think of something like that, then you would even, why that collides, you would even not know if it is a proper thing. And it is a valid question to think if it is a proper thing to phrase something like this. But okay, if you didn't understand that, that is okay. Just understand that empty set is a set with no objects. And if we have that is equal to empty set, and you recall the definition of set equality is just that this is subset of this is subset of this, and for that, again, we had to check mathematical statements, right? Mathematical statements involving implication in one direction, in the other direction, right? Just recall the definition of the subset on which the definition of equality of sets was based. In that case, if we have checked that and have found that this is valid, then we call the sets disjoint. Okay, let's go to the more superficial level. If the intersection of two sets is empty set, then we call the sets disjoint. And what it involves in detail, well, just use the definitions. Here we have equality. Equality was based on the notion of subset, and the notion of subset was directly checkable via the checking of the particular implications, right? Implications of what statements you have to look up. Maybe you know it immediately. And if you find out that this definition is actually, if you find out that this statement is actually true, that is, both implications are true, then you call the sets disjoint. Okay. Let's continue. Okay, yet another remark. When you start to look at the equality of sets defined as the subset relations in both directions, if you recall. For example, equality of sets, in this special case, you give yourself sets A and B. you give yourself those sets as being disjoint. For example, I don't know, A equal containing just two numbers, 1 and true, so equal to the set 1 true, B equal 3 4, right? And then you look and try to check that definition, the definition of equality of sets explicitly. And you recall that the equality of sets is defined as truth of the statement. And now recall how we defined that statement. That was defined in terms of the statements satisfied by the elements connected by the implication. And now here, for example, in this example, or generally when you prove some subset relation, but for example, in this example, when we try to check that, you will see that seemingly unintuitive definition of implication, where the implication is only false when the premise, that is what is before the implication sign, when the premise is false and the conclusion is true, that this definition suddenly does exactly the right thing. Namely, we have to prove the truth of this implication, right? In order to have established this. And the cases when X is not in M, that is for all objects that are not involved by the sets at all, not involved by the set which we would like to see be contained in that, or for which we'd like to check that. For all other objects that are not in it, implication is automatically true. So we don't have to prove those cases. Automatically true because the premise is false. Because when the object is not in M, and the premise X is in M is false. So we only have to check this. This unintuitive definition of implication actually yields that we only have to check the very reasonable thing, what happens when this is in this set. And the implication would be only true when this truth, that is X in this set, yields exactly that X is in the set N. Right? So that the truth of implication is given in all cases other than the premise is false and the conclusion is true. Sorry, I have mixed it up. When the premise is true and the conclusion is false, so from true we can't conclude false. In all other cases, the implication was true. This actually comes in handy here and gives a very intuitive situation where we just have to look at the case where this is true, the premise is true, and have to establish that this is not false, and then this is given. And this is very much in line with our everyday situation. If we assume that it is applicable here, we just have to check, well, if we want to have that this set is contained in this set, which subset actually means, as you can see here, right? We just have to check that for elements that are indeed in this set. And here you can see that abstract setting in play. You can see that concretely here, and you could look at the situation for those sets and explicitly write it down in terms of implications and see what I'm talking about using the definition of implication. Right. But of course, same would happen for every to-check subset relation, but just by this example, it came to my mind that I should direct your attention in this direction. Right, that's great. So the ways in which the logical operations work, or respectively the operations and statements, they are actually warranted by yielding intuitive interrelationships within the higher levels of mathematical structure. Of course, we would think that if it is the case for implication, well, probably it is the case for the more intuitive things, and indeed it is. So it all had its meaning, how we defined the action of logical operators, but that meaning might not have um, might not have to be seen within the framework of logical statements alone, but it is seen from the higher levels of mathematical structures that it actually makes sense. All right. Now we have, okay, we had union, we had intersection, and maybe we should also draw the diagram, but I guess you already know. It's just the elements that are in both sets. So if it is B, that is A, that is B, same as above, and that is the intersection. Right. Next up, we consider, well, I should think about it a little. What would be the logical thing to consider next? Oh, let's do first all definitions, maybe. Just like by the logical operators. All right. Now, let n be subset of n. And if I'm talking about subsets, then of course both of those are sets because I have only defined this operation on sets. So this is yielded by the context that both are sets, right? So I'm not saying, well, let's take sets n and m such that, because that is already encoded in me using this relationship. All right. Let this be given, and as I told you, the intuitive interpretation of that, which pretty much always applies when we have subset relations, so it's really what it is, but the formal definition is by implication. You should keep that in mind, but, oh, okay. There's the formal definition, there is the informal interpretation. Formal interpretation is this set is just contained in this set. Okay, now let this be given. We define and complement in M, and this is just notation, NCM is read and complement in M. Read a complement of N in M. So that is the complementary set that will, together with N, give M. So how it is defined? N complement M complement of N, or complement of N in M. And complement comes from complementary, and you'll see in a second what that means. Complement of N in M. And when it is just clear complement in what set we actually consider, we'll omit this index M. But okay, let's define it. It is all x in M, of course, it is complement in M, such that x is element of M, and simultaneously x is not element of n. So why is that we complementary set? Well, just draw the diagram to see that clearly. That is the set M, and that is the set N. And that is the complement. So the set M is divided in two types of elements. If we have a subset n in M, it is contained in M, right? And for each element of M, we only look at elements of M. We check, is this element in N or not in N? And every element of M, just like every mathematical object, we know that, but now we look only at the elements of M. Every element of M will be in N or not in N. That is, those two types of objects, taken all the objects of the respective type, and taken all the objects of the other respective type, and put together, will give exactly this whole set. Right? And this is the whole set M. That is the whole set M. The points inside it. Right. All right. More generally, define photo sets AB. The operation A without A without, and that is how I write without. You probably are familiar with this abbreviation. A without B as in the direction is this direction, backslash, right? Slash means something totally different, not in context of general sets, but in context of special sets. But okay, it is reserved for something different. That's why backslash. Okay, so what would you think that would be? Well, that is X in A. Or you could say, well, mathematical objects X, such that X in A and simultaneously X not in B. And simultaneously means that is satisfied and simultaneously that is satisfied for this X, right? And by the way, I wanted already to use this notation, but if it is just a general mathematical object, then of course we can omit it because it's clear that we could have written that, and we just write that. And for and, we write just comma because this just counts the conditions, right? We could also write it like that, but well, let's be formal. Write it like that. And you see, of course, that complement is a special case of that, where we just have already established that for the set that we take away, which is here n, this set is a subset of a superset. All right, if this set is a subset of something, then this superset of which it is subset, this set of which it is subset is called superset in relation to this set. This set is subset in relation to this set. This set is superset in relation to this set. But other than that, it is M without N. Just because of special meaning of this in many mathematical situations, we'll give that a special notation. But actually, it's just set theoretic difference. Not set theoretic difference, but set theoretic taken away. So A without B, this operation. But I think it is called set theoretic difference actually. Yes, that is called set theoretic difference, I'm pretty sure. But okay, whatever it is called. And you see difference because we just kind of take those elements away. We take exactly the elements in A, right? And when we take all the elements that are also in B away, or we just eliminate all the elements in B. For example, that would be A. And now not all points in the circle, but just this point. And now we look what elements are in B from those elements, and we eliminate them, right? That is element B, that is element B, that is element B, and all other are not element B. Right? And of course, when I write this, this is that this statement is true. The negation of the not of the statement X element B. But of course, when you interpret it directly, this will be the right thing to think of. But formally, it is of course this statement, right? And you see, I'm not stating those things explicitly anymore at many places because, well, as I said, you have to internalize those things, and it would hinder you to internalize them if I would explain every little abstraction step. And on the other hand, it would be a great handicap for getting somewhere forward with our discussions. All right, that is complement and set theoretic difference. Okay. What else do we need? Well, I think that's actually almost all what we need from the basic definitions. 2.4 Cartesian product. And why Cartesian? You'll see in a second. Cartesian product. What's that? Well, let A be sets. Define A cross B as the following set. That is the set of pairs and ordered pairs, which is important. That is an ordered pair, and we'll define it in a second. This is a new mathematical object. We have to define it yet, but for now, stay with me. Okay, and that is A, element A, B, element B. All right, and here AB denotes an ordered pair. What is an ordered pair? Well, that is a set AB. So we take the set with those two elements. But okay, let's not do that, because if we would take now same element in A and B, then that would be just set with A only, right? So remember our discussion of set notation and set meaning, right? An ordered pair, an ordered pair. that is the two not necessarily distinct, that is an important difference from a set, not necessarily distinct mathematical objects AB together with their order that is together with assignment of first, respectively second position. Because it is a pair, we have only two positions. So what does that mean? We take two mathematical objects and we say which one is first, which one is second. This is a new mathematical object that we have defined. And since it is together with the assignment, what it means is that is not the same as this, because the objects are the same here and here that we put together. But here the assignment is first position is taken by A, here first position is taken by B. So despite the objects taken into the pair being the same, the assignments are not the same, and hence we have no equality. And also, of course, if the object is just the same, like reflection of concept, when the object is just the same, then of course the assignment is same because it's just same object, but this is explicitly allowed. This is also a mathematical object where we just take two same objects, so it is not like in a set where we just difference one single object only one time, but here we can difference same object multiple times. But of course the assignment then has no meaning, because assignment of this being second or first would not change what would be the respective other position, because it would be necessarily same object taking this position. Right. Okay. Here again, I'm a little bit going into the detail into which people usually don't go, just to make you realize how you build the intuition behind it that recognizes all the mechanisms on which the thinking that involves the relationships we are discussing is built. All right, so, and let's look at a few examples, because usually this takes some getting used to this concept. Examples. A equal 1, 2, 3. B equal 1, 2, 3. And here I just draw a picture. This is not mathematically formal. This is just a picture to see what is happening. Let's say those are like elements of A. Those are elements of B. And then it's just convenient. It's just convenient to write it like this, because for element of A, like here, let denote A. Here, let me denote B, right? For element of A1, we just see immediately what elements of B can be paired with that, the lower limits of B, but with exactly 1, 2, 3. So we can go through it and we get so first we pair element 1 with all possible elements of B, right? Because this here says every such pair is given and it's ordered pairs, right? All right. So the first position is always taken by the element of A. The second position is taken by the element of B, but the elements involved in the pairs can be chosen arbitrarily when this condition is satisfied. All right. So that gives with 1 as element of A, we can pair 1 as element of B. We can pair 2. We can pair 3. With 2, we can pair again 1, 2, 3. And with 3, we can pair again 1, 2, 3. And that already covers everything. And this was just a convenient way to see what elements we have to cover in total. You can think why it works, but it's really simple. So Cartesian product kind of catapults us one dimension higher. Here we have first dimension, but of course it is very informal treatment, but kind of it catapults us one dimension higher. Here we have first dimension, if at least if we stay in numbers, right? This would be numbers in here. This again would be numbers on here. But here we are catapulted to the second dimension if we visualize it, because we would take points in here. And as you already guessed, the Cartesian coordinate system and the Cartesian product of two sets do not share Cartesian by coincidence, because Cartesian coordinate system as you know, it is just all pairs of real coordinates. And it's exactly the Cartesian product of this, where we always know what coordinate is first, what coordinate is second. This is, and we denote, for example, first coordinate is x, second coordinate is y. And the numbers in here, I mean, the respective sets from which we take the elements, the coordinates are, of course, real numbers, right? This is x, y. And if you would write it out, then we would have the set theoretic representation of the Cartesian coordinate system. And of course, I would also write it like this. And in the subsequent, I will use it without mentioning it explicitly, because it's clear what that means. All right, now let's take something different. I don't know. Remember, sets can contain any mathematical objects, in particular sets. That is the inductivity property of mathematics, that we can take the objects which we just defined and we can put them in structurally into the objects that we just defined, right? All right. Well, the objects here are the two object empty set and the set with 1, 2, and here we have just the object empty set. And do not confuse that with that. This is the set with no elements at all. this is a set containing an object. Which object does it contain? This contains the object, the set with no elements at all. But this is a set containing this object. This is not that. All right. And if you want you to do that, well, just follow the definition. Don't be confused. Go through all elements of A, put all possible elements of B there. All elements of A start by this element, all possible elements of B, only one element, all right? So next we just have that. That is one element of A. Don't be confused here. Distinguish the layers properly, the structured layers. Here we have two objects. This is the second object. And we have only one element in B, so we have to have a second pair. So it's two pairs. And as you can already guess, of course, the number of elements, if the number in A and in B was finite, will be just the product of the numbers of elements, clearly. It's just, yeah, it's obvious. All right. Well, what else would I like to say about that? Okay, Cartesian product. Cartesian product. Right. Quotient. Quotient. In general, because the rows in the pair are interchanged, right? But if A is equal B like here, then of course it would be just same elements. Mathematical objects involved are the same, and we just would have that in total, we would have all the same orderings covered. But here, for example, well, then the first element will be always empty set. Here, nothing would change, of course, we would just switch that. But here, the first element would be that, and they call by ordered pairs. We don't have commutativity of elements. The assignment of first, respectively second position is important. Right, okay, I think that is all operations on sets that we will need for now. Right, so we had the union, we had the intersection, we had the set theoretic difference, and we had the Cartesian product. Right, if we will need something in the subsequent considerations, then I will just introduce that. All right, then go on to talking about properties of operations on sets. Right, and here, well, of course, recall that the operations on sets were defined via application of certain mathematical operators, that is, operators on mathematical statements in this context, to certain statements of being contained of elements in some sets. So of course we have that some properties will carry over from properties of statements. Maybe you don't see that it is, and of course, that's why we will discuss it a little bit, but not that extensively, and you will see that there's really no need. Commutativity, associativity, and this of both, of union, and of intersection. And you should already know what we are talking about. Union of A with B is of course same as union of B with A. Well, let's do it properly. That is commutativity. So structurally kind of same thing as commutativity statements. Of course, commutativity in any context will be something like this. Structurally, that we apply a thing, and wherever we apply it to something in that order or in that order, doesn't matter. Okay, if something put in that order, in that order, doesn't matter. And associativity, well, same structurally. And you will see that it's really the same, but of course, if you don't see it right away, it's okay, because of course it was a lot of abstract machinery. So it's no wonder if you don't see it right away. It's normal. But you'll see in a second that it really is nothing, and though it might give you an impression like it is very abstract in the beginning, but let's just look at what it is. Well, we remember what is equality of sets, right? Equality of sets is defined as subset in one direction, as subset in other direction, right? So, but let's, before we prove this subset in one direction, subset in other direction, just look at those sets. Just by definition, this is the set of all x such that x is in A, or including or, be cautious, x in B, and B union with A is that thing. Well, maybe you don't know what to do. Kind of, you see that it is the same because it's commutativity, but why can we just say, well, that's the same, even though it's descriptions of different sets and then the sets are equal? How does that work exactly? Well, you see, we have to prove both things, right? We have to prove first, and that is a shortcut, and I will write only one time that. That is a shortcut for this, that I am now proving this direction. I will just write it like that always, right, in such situations. All right, what do we have to prove? To prove, and after our discussion of the conveniently defined implication, we just have to prove that in the case when it is really an element of this, then it is an element of that, right? And after our discussion, we know that we conveniently can only look at the case where it is really an element of that. We don't need to consider a case when it is false, because the implication will be always true, right? But you see, an element of this is exactly all the mathematical objects just by definition of set. It's exactly all mathematical objects which satisfy this. That is, in particular, when this is a subset of this, when this is an element of this, and the set is defined as the set of all mathematical objects X satisfying this, then this implies, of course, just by definition of the set, that we have that. So this, having that this is element of the set, implies that, of course, that element satisfies the set condition, because that means being in this set. It's exactly what being in this set means. Right? So this implies that. But now, this, we know the commutativity, right? So we know that this is equivalent to, the commutativity of the OR. Using the commutativity of the OR, we just know that this statement is actually equivalent to this statement. And you see, we already use equivalence like equality without even talking about it. But now we have equivalence, but we want to have implication. But what was equivalence? Well, the equivalence of those two statements is actually equivalent to this statement being valid. Recall equivalence, right? And you see, we already interchange the layers of interpretation and argue on one layer and on the other layer simultaneously. The equivalence was in itself equivalent, and that is equal to simultaneous implication in the one and in the other direction. Right? That we had just from property of the OR, that it is commutative. So this statement was the same as that statement. But the equivalence could be rewritten as simultaneous thing of this statement. And that I have written instead of truth of this, of course not OR, but this AND. So actually it would be this large statement that we have this implication and simultaneously we have this implication. And you see, and simultaneously, I'm already here on the second layer of interpretation when I refer to that statement and I say that and means simultaneous truth. But it does, because if we go to the definition of and that connects to statements, then it is true if and only if this, in that very case and in no other cases, when both is true, so that we can use it as talking about simultaneous truth if we want to have this statement being true. So that I can really talk about it as and in sense of the intuitive interpretation and this is true and this is true. Okay. But if this is known, this is just known, this is implied, so, and this is assumed to be true, so this is true, so this is valid, right? And this is equivalent to this, right? And the equivalence itself is equivalent to this being given and this being given simultaneously, which means that we can replace this equivalence right? That implied that, and that was equivalent to that, right? And of course, you have to pay attention how it worked. It's like, yeah, okay, it's not quite clean, right? This implied that, and we know that we only have to consider the case of truth of that. And the case of truth of that implied that, right? Just because this is the property of an element of the set, because it's exactly the elements in the set that satisfy this. So this implied that. But then I have written that already here But I should have written, if I would have written cleanly, I should have written, but no one does that. It's just such a drag that no mathematician ever does that. We omit a lot of things. And we make a lot of things shorter because it's just, well, that's self-explanatory that we mean that. But okay, let me write it very cleanly. That implies that just because this set is defined like this, it contains the objects that do that. So of course, if it is in the set, then it implies that, right? And now we have that this is equivalent to this. So this is another line of thought, so to speak, because that we had by the commutativity of the OR. But now the equivalence itself, this equivalence is equivalent to, and if that is valid, because that is commutativity and it is equivalent to something, then what it is equivalent to is valid. That is truth table of equivalence, right? But we already use it on the higher level of interpretation. And both are valid. At least the end is valid, but I'm not writing that as end. But I think of that as end. It's more self-suggestive to write this parenthesis. And this big one. All right. And now we had that the equivalence of that was equivalent to that simultaneously being given. And that was established as truth. So that was established as truth from here, but that was equivalent to that. So that was established as truth via equivalence. Yeah, okay. Already to talk about it is really like, we don't do those small steps usually, but okay, I will do it for you. So we have this element is element of that, and we know we only have to consider case when it is true, but I will do it fast. Then this is given because this is the property of this element. This is what characterizes this element. So of course this element satisfies this property, and if that was true, then this is also true, right? So now this truth is given because that's just the property of commutativity of OR, which we have had earlier, right? Commutativity of OR. This commutativity of OR is equivalent to this, which means simultaneous validity of this and this. But simultaneous validity of this and this means in particular validity of each of them taken alone. And we take this one because we are interested in it. They are both valid, but we are interested in this one. And I could just write the statement, but I will even write for you is true, which is actually really never done because there are just too many layers and we don't look at them explicitly. We just do them automatically, right? This is true. But if that is true, and that is true, then we can take this being true and from that implication that this is now true, we can go from here to here, right? And we can use that because this implication, I should also write that this implication is true. And this is known to be true, then this is true. This is finally true. Okay, maybe you have already forgotten where we started. We had the truth of that because it sufficed to consider the truth of that to establish the implication which we wanted, right? then we have concluded that this is true because this is just the property of each element in here. So if we take an element of here, so that is true, we have taken an element of here, then it has this property. Then we had the commutativity, and we could have written the commutativity as validity of both statements that and that simultaneously, right? Since we had the validity of both the statements simultaneously, we could conclude from that each of the statements is valid, but we were only interested in one of the statements being valid, and we took the statements in which we were interested in being valid because this was valid, and we took this validity of this statement that this implication is true. But now this was known to be true from here, and so given that this is true and given those truths, we can have that this implication is true, meaning since this is now true, this is true, and hence this implies this, and this implies this, meaning that is true, then that is true, then that is true. And that is what I have actually, if I would have written it normally, like it is done, I would have written like that. All those steps are usually never done, never ever, because it's just too obvious. But in the beginning, okay, I'll do them, and maybe it is in the beginning even more confusing than if I would have just left you alone that formalism. So usually you write like that. But in the subsequent, you will see that if I would have left you alone with that, then those questions just would have arisen in other contexts. So you would come to realize all of that eventually, but not to the whole extent. That's one thing. So there would be like gaps for a long time, and not necessarily all of them. But now I have just shown you everything, and I won't do it ever again because it's like it's never done. You have to get used to this type of thinking. That's the only way. So usually, instead of all of that, I would have written just that. All right, and now we know we consider the case that is true, then that is true, and then that is true because of those truths, because we were able to conclude those truths, and then hence we're able to conclude the truth of that from the truth of that, right? And now that being satisfied by our x defines it as element of this set, because that's exactly the mathematical objects that have this property of satisfying the statement. And hence this is again equivalent, and we could do same game with equivalence because it doesn't matter what statements we take here, but I'm just writing equivalence here without thinking about it anymore. X element B union A. And that finishes with proof of 1, right? And usually I would have just written it the highest with sequence. I would even not have written that. I would have written that because this is self-explanatory, right? And well, yeah. So you see, I'm using the properties of logical statements pretty much like it's nothing. And this is how it will be done, and it will be kept even more on a higher level of abstraction. So this is just obvious things, right? Okay, so we have proved that, but this was only one implication. Sorry, that's not the proof is not finished. But of course, can do that because this is exactly what characterizes elements of this set. And characterizes means if an element satisfies this, then it is in the set. And if it is in the set, then it satisfies this. So this is in both directions. And we could do same game rewriting the equivalences as both applications being valid simultaneously, and we could pick at every round, of course, also here, because this is how the set is characterized. You could pick in every round the implications that are interesting for us, and to conclude with truths, because we just start by the truths, because the truths, the cases where it is truths, are the only cases that are interested for us to checking implications, the only cases where premises are true. So indeed, the proof is finished. And usually what you would have seen in a mathematics course, you would have just seen just implications written down very quickly in 5 seconds, and the proof is finished. And that's what I'll be doing from now on in most cases, because it's just too much of a drag. So we have proved both directions. The other directions would be just implications, and there they are covered by those equivalences. You see, if you can write those equivalences, then it makes it much easier to prove implications in one and in the other direction. By the way, another remark at this point, concerning proofs. We have not really discussed what a mathematical proof is, but in truth, it is a sequence of implications. So here you have seen both proofs of both statements, right? That and that, but well, in what sense that is a sequence of applications? In what sense has it been a sequence of applications here? Very simple. On the highest level, so to speak, our proof did the following. On the highest level of abstraction. Maybe not on the highest, but on sufficiently high. Establish truth of this. This is what we have done. Very explicitly. More sloppy, but nonetheless correct. And how it would be done mathematically, we have also established truth of that. Now, we know from the definition, and definition always means equivalence, that means that. I mean that together, right? Right. Now we take, we have established truth of that. We have established truth of that. And now we take only the implication, because we don't need the other stuff, right? And this was the single implication which we have actually shown in this proof. We have shown that what we wanted to show was this, but we have now split it into parts. Why were we able to split it into parts? Exactly because, by definition, the validity of both parts simultaneously implies the validity of this statement. So what we actually have shown was the implication of the statement that involved two statements implying one statement. And of course, the truth of the end, again, is only when both statements are true. That's why we had to show that both of the statements are actually true. Okay, it's it's a lot of words to just state that we have proved this implication. But because it is like I'm trying to be explicit, not abstracting it anymore, I'm talking about this, but here that is C, that is D, and we have proved that implication, that is E, right? So we have proved the implication of two statements valid simultaneously, implying that statement. And what we have proved, well, this implication is just given by definition of that, right? The definition just says that this is if and only if. This is the definition of equality, right? But we concretely, this equality was realized now for some arbitrary A and B, and we didn't know that the equality was realized. And we have written the relationships between those sets A union B, B union A, which would imply this equality which we'd like to prove. Right? We have written some two statements, namely this one and this one, whose simultaneous truth would imply the wished equality. Right. And here I call this C, I call this D, I call this E. So what we did on the highest level structure, we have established this implication. But have established this implication in what sense? Well, this implication was given by definition. So that this implication is valid is given simply by this definition. But we have established the truth of this implication in the sense that we have given sets A and B, and we have shown that indeed the implication gives always true. So the implication itself, as the connection of that big statement and that statement, that implication is true. But we had to establish that the premise is true in order to have that this implication always gives true. Because if the premise would be false, we recall the definition of implication, then it could be true or it could be false. So we wouldn't have said anything about that. We would not know. For some A and B's, it might be true, it might be false. So we had the implication itself being true, but we had to establish that this implication really gives the truth value. So the implication was true in the sense that those two big statements connected by implication. That gave truth value, that gave the truth value true, right? So no matter what we put in here is A, B, we always get that the implication value is true. But the implication value is true could have been also given when that was actually false. And then that could have been true or false, right? And we would not have established that really for all A and B, not just the implication as the relationships between those big statements is true, but really the implication is true in sense that this is actually the true statement for these sets. For that, we had to establish that the premise is always true. Because if the premise is always true, then we know the implication could not imply false, because the implication itself was true. And if it would have implied false, then it would be false. The implication itself would be false. But it is not false. We know the implication itself is true. So that would be always true. So we had to establish the total truth for this, for any A and B. Right? And that was the main implication, which we proved in that sense. The implication itself was given by definition, but we proved that what will result, given this implication by definition, will result then in actuality of mathematical reality, this statement will always have the value true, given that this implication is actually valid. So the implication was valid on the higher level connecting the statements, and that is what we used to establish the truth of the statement we wished to be true for any two sets. All right, that was a lot of words, and it is really not easy to explain, and you will find such explanations nowhere. But as I told you, I'm giving such explanations because I want you to think about it a little. If it confuses you, okay, just try to think about it calmly. If it doesn't work, okay, just take it as it is. But I would be glad if you would think about it a little. So on the higher level, we have our implication, and that is valid. But we want to establish actually the truth of that, and we would use the truth of this implication that is given by definition. And we would use the truth of that implication to actually establish the always given truth of this, because that means that this relationship is valid. That is, it is always valid no matter what A and B would take. All right. And using the truth of implication means we had to establish for our premise, that is the way that we have chosen, that is one way how to prove this. We have to establish for our premise that it is true, or that is the way how we have chosen to establish the always truth of this. So if this premise would be always true and the implication is known to be always true, then that would be always true, and we would be done. All right. And this is what we did. We established the truth of this premise. But now this was the bigger implication, and within that we had smaller implications. We had to show that this is actually a subset of this, which was showing an implication. And how did we show this implication? Remember that in the equivalences inside of that there are implications. We have shown implications, right? So a mathematical proof is actually a sequence of already established implications or of implications that we establish on the way. Like those implications were established on our way. We first realize the equivalence, then we realize that that establishes already the implications. So it is a sequence of implications, right? And it is a sequence of implications. We said that, but the important part is now that it always suffices to consider the case where the first premise of a sequence of implications is true, because we want to establish all right, here is a twist. You see, in this example, we have seen that the implication is already true, but because by definition it is true, just by this definition, this implication would be true because this equivalence is true, right? This is just the definition of that, right? But usually implications should or might have to be established, right? That can happen. For example, like here, we had to establish this implication, but already we replaced it by equivalences in the subsequent considerations. But okay, we had to establish this implication, right? So, and when the implication is established, that is, the truth of the implication is established, then we can use the truth of this implication, just like we did here, where this implication was already known to be established by definition, right? We can use the truth of this implication to have our consequence being true if we have established that this is true, because if we have already established that implication is true itself, and that is implication between those two statements, that the implication itself is true, then to establish the always truth of this, we have only to have always truth of this. Because if we have always truth of this, if the implication is true, then the only way how that could be valid is that this statement is really true. Because if it would be false, then the implication could be true if it is true. But if it is always true, and correspondingly, that means this is always true. So a mathematical proof is establishing or using establishing a sequence of implications and establishing the truth of subsequent premises based in each step on the established truth of implications. That is, we start by some true premise, of a premise that we supposed to be true, because that is the only thing we have to check. Then this is true, and we establish the truth of this implication. It might be established by definition, it might be established by us, we might just show that this implication is always true. And then, knowing that this is always true, or more precisely assuming in this case, we establish that this is always true. And when we go, this implication always true, and so on. And then we arrive at the final conclusion. And this is final conclusion. This is how mathematical proof is structured. It might be very well hidden in sense that it would be very difficult to write the structure explicitly, but yeah, that is actually how it always is. And then we say that this is truth, and we claim that this is truth, and we are allowed to do that because if we started by true premise and we would have ended by something wrong, one of the implications should have been wrong. Because if in each step it is true, then the next step should be true as well. It's just logic, right? Intuitive logic, right? So we can't arrive at something wrong in that case. That is, even if you can't maybe follow through all steps of a proof, there might be 100 steps. When you have been following this procedure, establishing implications, establishing truth of premise, concluding by the truth of premise and truth of implication that something is true, then you will have arrived at something true. And that, if it is the conclusion that you wanted to conclude, then this conclusion is sure to be true, at least within the mathematical modeling realm. But it turns out that this realm is really intuitively consistent. But yeah, this is how mathematical proofs work. All right, very important discussion. I didn't know that I would do it by this example, but yeah, so that you now understand how mathematical proofs work. And that defining the implication like we defined it was a very special trick, right? That was the trick because, well, we are only interested in starting at true premises. We start at false premise, everything could come out. We want it to be like that because we are not interested in starting at false premises. We are only interested in starting at true premises. And so we want to capture that starting at false premise could give anything, meaning that it would not say anything meaningful. Because if it could give anything, well, then we would not know what it actually gives. But starting at true, it gives only truth. And establishing true implications, starting at truth and having all implications established as true, it gives only truth. Alright, maybe it was a little bit abstract, but I hope that you could follow that nonetheless. And of course, the other things like true, okay, maybe I confused you, so I will do 2 and 3, for example, but the other things you have as homework, because, yeah, because it's very simple as you've seen. So the proof of 2, this is just defined as x such that x is simultaneously x in A and B. Now you'll see how it is done mathematically. It is not done like I did at all. right? Oh, right. I have already. You recall that we have now to prove A intersected B is equal B intersected A, and I just immediately write those implications, right? X B, but of course this is also equivalence because that is how this set is defined, right? So that is equivalent to X being in the set, and that is equivalent to X satisfying the property that defines the set. And now we have the commutativity of the end from the considerations of logical statements, which gives that this is equivalent to this and this. Okay, same way. I'm just doing, so this I'm just going in the different direction where that is switched, but from structure it's the same, right? So you can already immediately see that that is the case, and we have established it. And recall that the implications are hidden in here, implications in both directions, because equivalences just work like that. And again, equivalences were defined like that, of course, so that they can capture the implications immediately, right? So what else? Well, associativity of union. Okay, here we have three sets. I maybe will use now already some shortcuts. Let's see if it works. That's just the set where we have x, right? And because just that I wrote this parenthesis, I don't have to. The interesting thing is what I mean, and it is clear what I mean, so I could have written parenthesis here. So the notation itself has only to be exact and precise in case that we understand exactly what we mean, but it doesn't have to be like formally precise, like you have to draw any parentheses and things like that. No, it's not like that. As long as you stay precise and exact, it is not like that. So now, of course, I could shorten those considerations because it's just, well, I consider those elements anyway. So I consider how those elements behave. So I could immediately switch to considerations within sets because, well, the sets are defined in terms of elements, and an element satisfies this statement even only if it satisfies this statement. But the sets containing elements are defined exactly as sets of those mathematical objects that satisfy those statements. So if the statements are equivalent, then of course the sets are equal. So we could have spared us all this nonsense writing it down. Of course, you could write down it here again, and it will help you realize that it really works. You could do that, and maybe you should do that if you don't see it explicitly, but I won't do that anymore. Just equivalent statements, just because the sets are defined in terms of elements satisfying those statements. Equivalent statements define equal sets just because those implications are actually immediately seen to be valid in one and in the other direction if you write it out. Okay, so and that is of course the set just by definition. Okay, here I did just two steps at once. I should consider that set and that I unified with that set, but you could have written it out explicitly. So I have here a union. First, I have that in the brackets, and that is a set of all x satisfying xb or xc, and by that I mean x element of b, x element of c. And then I use this definition, and of course I have brackets here like that, but I have done it in one step. Okay, so and here I continue, and here of course same way I just see that this is that. But of course, you could have written it out explicitly. Nothing hinders you from that. I won't do that. All right, this is proved. And 4 is, of course, homework. Just write it out explicitly if you like, or do with short notation like here. I would recommend to write it out explicitly because you might think that you understand, but when you try to write it out, you might not be able to. You could always also, or not always, but you could also try to write it out in that way, but don't do that formally. If you do that like that. I'm thinking what I should do to do this and that step, and not like, I should guess what I should write here to stay formal. No, just ask yourself, just wonder, just do wonder how it works, why it works, and write down things that explain how it works in precise mathematical terms. Do not guess, well, how do I have to formalize that in order to match what he has shown? No, not like that. Just stay faithful to the logic and not to what someone has shown. But of course, that supposes to understand the logic, and that is your task. You have to do that. Right. But never try to somehow match what I'm doing. That is the worst thing possible. If you understand why it should be matched exactly at each point, then you could write what I have written without looking at my notes. Not exactly, but what I'm trying to say, and you won't just try to write the same. You will understand that, oh, I have to write that and that. Maybe I don't know how, so I will look up how he has written that. And then I see, well, he has written it like that, and that makes sense to achieve those and those means. So yeah, that is how it can be done. But not in the way he has written it like that, it has to be written like that, always. Never like that, okay? Okay, that finishes with proof. If we take your homework in account. All right, that was a lot of remarks and a lot of discussion for this short thing, but I'm glad I did that because, yeah, now you have seen how it really works. I mean, how proofs work and how implications work and things like that. It is good that we have discussed that so that you have clear understanding of that, or at least you have all the building stones to build this understanding. So you won't be blind in that sense. You won't be conceptually blind. If you'd like to understand that precisely, you will. All right, what is next? Oh, what was that actually? That was commutativity and associativity of union and intersection. Okay, so 2.3.2. Distributivity laws. By the way, of course, for all such set operations and their properties, you can draw the Venn diagrams, so those with circles, right? Right, just like we did for operations itself. For union in this section, we have drawn the circles and have thought of sets graphically. You could do the same. But well, you can do that if you like. I won't do that. A, B, and you see that just mimics what we did in the part on mathematical logic. You can write it out if you like. I would probably also recommend that, but there's no need to do that for me because, well, you know how it is done now, right? Okay, that's intersection of P and C. Right. And that's just mimics those distributivity laws we had for the and or, right? If it does not, then I have had a typo, right? A, C, B, C, right. And that is, of course, again, for any sets. A union C intersected with B union C. All right. Right. Of course, the proof is homework, and don't think that I'm somehow avoiding proofs because I'm too lazy. It's just that it's not that interesting things, and you probably can already see that this is just what we had as rules for logical statements written in the set language, so to speak. If not, just look up the rules we had for logical statements and compare that with the kind of proofs we did above. It's just that I don't want to waste time for looking at such things that are rather straightforward technical. It's nothing but technique behind it. Of course, from each such proof, you could learn something if I do it, something that, well, something that might be not trivial for you, but better do it yourself because both approaches have some advantages and disadvantages, and at that point, it's better for you to collect experience in doing such things and thinking about such things. Just like here, just think about it, play with it, internalize it in all ways possible. Think why it makes sense, why it is defined in those ways just like we did with implication, how it works, what familiar sets you might take and do it with them, and things like that. It's better you do it that way than when I just present the proofs, because by those proofs there are really no ideas involved, just stupidly writing down the things that we did in the statements and basically translating them to the setting of sets. That's it. There's nothing else in it. Okay, and De Morgan laws, same thing. Just have a well, what was that actually? Yeah. Okay, of course, in De Morgan laws, we just had the negation, right? But negation would be complement. The complement should be in something, right? So set theoretic difference, and we had to add something here. But what it would mean, well, exactly that. And you have that, and you have that, and you have to change what you're doing. You have to change. What did I tell you? You have to change. What did I tell me in that case, right? You have to change. And here, same thing. And this again, just a bit resets. By the way, you might be confused. Well, what happens if I take from a smaller set, a set that is larger than that? Well, nothing special happens. This set just disappears. Larger than that means that I take from a subset of a set, the set of which it is a subset. Well, I take away that. I just look at the elements that I see. Oh, all elements in here that are not in here, and such elements don't exist. So empty set results. Right. So that's just as a note. But of course, we would not necessarily state all such little things. You just will have to discover them by yourself. Right. Well, let me just prove it quickly. Of course, I could say again, it's homework, but okay, let's prove at least something. But you don't say I'm not giving you any proofs. That's just x and what? Well, that's x satisfying what? That's x satisfying c, right? Because that's how it is defined, x and c, and x is not in here, right? And simultaneously, there's just definition of a set theoretic difference. X is sum of a, and x sum of b, and that is with not, right? It's just how set theoretic difference is defined, but also the intuitive interpretation is same, right? So here you have and here you just turn it upside down, as you recall. Well, I usually have written that in another direction, I think. Doesn't matter, but okay, let's stay consistent in our notation, even visually. Okay, then turn it upside down, the Morgan laws for logical statements, right? And then we just have to use the distributivity law, and we have to use the definition of a set theoretic difference. Again. And of course, we have to use the definition of union. So we're just dealing with logical statements again. Maybe it's like a lot of operations at once, and so it appears to you like something complicated, but it's just your first case at that. Of course, it mightn't appear something complicated, but well, you just have to get used to it. Just have to get used to the circumstance that it is just something which is done automatically, right? But of course, there's time to get used to it. It's normal. And the second one is homework, of course. I just do same thing. Okay, then in particular, of course, it works for complements because complements were just something in some set. But if you like, you have to write it explicitly how it works, how complement was defined, but you can just remember that complement was defined in sense of set theoretic difference with that set, and so of course that's nothing else but that. And this is complement in some set M, right? So it kind of we complement we pay by the switch. The set theoretic difference we pay by the switch again. So just like by the logical statements, right? So that's a union, and we apply complement, and we get all right. So that is proved automatically by that because this is nothing but a special case of set theoretic difference. All right. So 2, 3, 3, 2, 3, 4. 2, 3, 4. I don't even know what else we should do about sets. I think we're finished. But let's think about it a little more. Well, I really think we are finished concerning sets. Alright, well, let's think about it a little. Yeah, that's it. I don't think there are other things that I'd like you to look at explicitly. Of course, there are a lot more identities between sets, but you have to discover them by yourself in the respective context where you will need them. Right. Alright, so now we are by part 3, and that's quantifiers, if I recall. Hmm. Let's look at that. Oh, I have done a lot. Okay, where was it? Alright, there. Yes, we quantifiers. Alright. Ah, that's finally topic where we'll look at something that really has to do with serious maths explicitly, so to speak. These things are involved in writing down serious maths. Of course, sets are by default immediately. They are everywhere. Logical statements too, but those things they really are like signifiers of university math. The elementary signifiers of university math. It might be the first thing one would think of when thinking, well, what does signify the university maths? Quantifiers. Because it's like a very strong symbol. Right, 2.3 properties of operations. All right, so yes, that's indeed 3 quantifiers. 3 quantifiers. And of course, mathematical quantifiers are not about just some finite quantities. On the contrary, they are about existence. Not about quantities at all. They are about existence. Well, all about quantities, special sense. Right, quantifiers. Well, what does that mean? Okay, let's look at that. Definition. There exists and you can't really define that thing. You can in abstract theory, but you cannot really without doing some really abstract stuff. You should just understand what it means. This is written like that. And we will look at the syntax, of course, but what that means, well, it's more like definition. Uh, it can mean two things. In a given set, there is an object with specified properties. Or some object, and of course by objects I always mean mathematical objects in our discussions. Some object is not leading to contradictions. When introduced. And you don't think to think about that too clearly or something. You just have to get used in to how we treat this quantifier. This is called the quantifier of existence. Some E reflected on the vertical axis, right? Some big E reflected on the vertical axis. You don't have to think about it a lot, but well, that is the usual case when we talk about that, and this case can be seen as this case if we take, but that would not be a set anymore. You could look up that there are problems with defining certain sets when the collections of objects become too large. This is some other collection and some collection in the very general sense, and then you could consider this also as that. I mean, you could consider this case as that case, just like in this collection of all mathematical objects, whatever this collection then is, is an object with specified properties, and that kind of means existence not leading to contradictions in general. But well, so this can be considered a subcase of this when the collection you look at is large enough. But then, of course, here arises the question of how to specify this collection, and it can't be answered that directly. So you just have to get a feel of what it is. So knowledge or an intuition that is exact enough to deal with mathematical concepts. That's why I call it definition. There exists, well, let's look at some examples. Examples of mathematical existence. Well, there exists a set A, and that is existence such that here I specify the properties. So there exists a set, of course there exists a set that is just an axiom. That is, by the way, an axiom that sets exist, that sets are supposed to be existent objects. But I'm not writing it down because we are not that interested in stating that as an axiom, such that the number 1 is element of A. Well, we could write it down in mathematical statement, right? So quantifiers are just parts of mathematical statements. And indeed, it is a true statement. Take A equal to this set, and this set contains that, so it does exist. All right. The other part is difficult to illustrate on elementary level. because we are always having some kind of reference to some set in which it should be, right? But okay, let's say I'll try to give you an example of that. Um, like there exists. Oh, by the way, that's you could already say that this is an example of that. I just noticed. Because this is like it is not in somewhere. It is if it is in a set, then it is in set of all sets, and that set does not exist. So that is already an example. So example is existence of sets, for example. Of course, it is like a trick. Set of all sets does not exist for a certain reason because it is descriptively given. And you can look up Russell's paradox for set of all sets. I'm not doing that because it's like so trivial, but Russell's paradox set of all sets can't exist. But okay, I'll give you uh, something about it. Imagine a barber shaves all those who don't shave themselves. Does he shave himself? So it's called kind of like a property of the barber should place him within the set of those who he shaves, but simultaneously can't place him within the set of those who he shaves because him obtaining this property would automatically place him outside of this set and vice versa. So, yeah, that's like that. And with set of all sets, you can construct similar things. So yeah, there's no set of all sets. And if we restrict the collections to sets, then there can't be set of all sets. And that's why this is example of this if we take a set. But okay. And get caught up like that. So we have an example, but let's just, well, there exists a smallest even natural number. Recall that 0 is in natural numbers. In our case, if it wouldn't be, it would still be true for true, but 0 is natural number. In our case, it is even. So yeah, that does exist. Now take something there exists x, I don't know, in real numbers. Let's take some wrong existence statement. Because, oh, that's mathematical statement. So we can be right or wrong. It doesn't prevent us from stating it as long as they are stated reasonably, right? Such that x squared plus 1 is equal to 0. We know that it is not true, and we can prove it easily, right? It is not true because x squared is always bigger or equal 0, 1 is always bigger or equal 0, and both bigger or equal 0 gives in something. Sorry. 1 is bigger than 0, that is important here. And then we have that this is always bigger than 0 as long as x is in R, right? But this is just a side note. So this is also a statement of existence, right? Also an important quantifier, but I do not introduce it separately because it's very so-suggestive. It does not exist. This was a wrong statement, right? So that was false. There does not exist an x like that, and this is a true statement. And you see, in some contexts, stating a statement means asserting its truth, that is, this mathematical truth. It is context of proofs, for example. Unless you state something like assume it's true, then it might be also false. So you see, you should keep in mind the context. Here, you have a quantifier slashed, and that means that there does not exist an x in R such that x squared plus 1 is equal to 0, and this is a true statement, really. Right, okay, that was the existence quantifier. Nothing special, right? Yeah, the interesting things begin when when you have mathematical statements denoted by many of the quantifiers. You might not see yet what I'm talking about, but you'll see soon. Soon enough. Right, because it becomes abstract pretty fast. Right, all right. Definition next exists. Next for all. Definition. For all quantifier. Well, for all quantifier that is denoted like that, and it asserts, might be true, might be not, we just can construct mathematical statements with that. It asserts truth of a statement but it asserts, so we claim that it is true if we write that down, but it could be not true if it is wrong to assert this truth. It asserts truth of a statement for all objects within a pool of objects, and the pool could be all mathematical objects. For example, you'll see in a minute what I mean. In a pool of objects. So example, I could say for all x, and now you'll see the interplay of quantifiers, now harmless, but well, it will become there. So for all x, there exists a set A such that, so you see, for all x, so we fix an x out of the collection of all mathematical objects, and we claim there is a set A such that x is an A. Well, of course, take a set that contains this object. And, and here, if that is true or not true, well, take the, okay, we can't take set of all sets, but you can think that there are problems, but we can state this, right? For all x, for all mathematical objects x, and for all, this is very important. For all means check for each one. check for each one separately. Then assert based on totality of results. This is very important because for all could mean there is a set A such that contains all x. That is not that. When this quantifier is there, that means check for each one separately. So we take first mathematical objects, check it. Second, check it. Of course, we don't do that, but abstractly we do. Based on totality for, then assert based on totality for all results of checking of all results. All right, so we go through it, and that is the sets A could vary. So if I wanted to be pedantic, I could say that this A could depend on X. And of course, for example, this choice, this statement might be true, might be wrong, we don't know yet, but this kind of suggests it's true. And this choice depends on X, of course, because for each X it would be different. Like if we take Y, another object, and I mean another object, not just another symbol for the same thing, it is excluded, it is same object, it is not same object, it is different object. And we take Z, so that indeed depends on that the object is different depending on what we take. And this is, you go through each one separately, you look at what comes after that to establish the truth of that. You look, well, there exists a set, that is, you go into the collection of all possible sets and you look through this collection. Do we find at least one? Then you know, well, we found one. Okay. Then you have finished checking for this one and you go to the next one and the search starts new. That is for all there exists. Now another thing. There exists, that is, you start your search and you pick one object and you are able to pick it. So you go into the collection of all sets, not into the set of all sets because it does not exist, but into the collection of all sets. And you pick one. If you are able to. You don't know if you are able to, but this asserts you are able to pick such one. To pick such one. You check for each one, but you are satisfied when you find this one. But here you had to check for each one of them separately. Here you are satisfied if you find this one. And mind the difference. Mind the difference. Here you check for all and you pick exactly one. Even if there might be multiple, you pick one. And now you picked that one and this one is fixed. And now you go here and you check for each x if that is true for this fixed one thing. Here you have chosen one thing and you check for all x for this chosen thing. So it is important what you are fixing. Here you are going through all x, and for each x individually you fix the x and you look, is there such a x? Right? Here you fix your a, and if that is true, then you have for this fixed a to have that if you separately check for this fixed a for each x, if that is true, that has to be true for this statement to be true. You see the difference of two statements. It is very important what you are fixing and what we'd like to express being fixed, that is encoded in this order. And the order is, of course, self-suggestive, as you see. If we have first for all, then of course we have to go through all separately, and the order suggests what we are fixing first. First, we are fixing here an X of this collection for all. And when we go and we are allowed to pick any one that fits. Here, we pick any one that fits, but for what? Well, what we fix this one. And here we have, well, this fixed, again, this is here, this is fixed. This one is fixed. And we look through all of them and check through all of them for this one. So what is fixed? Here, this one is fixed, right? And the question is if we find such one so that if we fix that, that satisfies that. But here, the thing is, we go through each of them, and for each we could pick one so that it satisfies that. That is the difference of when the respective statement, this statement or this statement, is true. Right. And of course, we have that if this statement is true, then this statement is true, but we do not assert the truth of any of them. It is problematic, but we could just write this implication is valid. When we write implication, then we mean implication is valid. So we claim this implication, and indeed it is valid because you see, if that is the truth, and that is the only thing we have to prove to have the validity of application, as you know, because false always gives application true. So if that is true, and that is of course true because for each x we could just take ax is equal to this a. So if we find such a in which every x is inside, then take an x, and we know there is an a in which every x is inside. So in particular this x, because this is all mathematical objects, this is all mathematical objects, so we have a set in which all mathematical objects are. So we take a mathematical object, and we know this object in particular is in this set, so we take this set. Right, so all ax, when x is a, and so here they are not distinguished. So very easy with quantifiers when you discuss them thoroughly, but confusing when you just put them there and don't talk about them at all, like it's usually done at university, as far as I know. Well, I should not say that because I think in my courses it was pretty decent. Of course, it didn't go into such level of detail, but nonetheless. All right. And of course, it does not alleviate the difficulties you will face by quantifiers, because this is child's play, right? This is child's play because you see things like for all. No, let's take something simple. For epsilon, this is just an example of when things with quantifiers seem to become a little bit messy, at least when you encounter it first time. There is delta bigger than 0 such that oh, okay, what would you like to do? For epsilon, there is such delta such that whenever our distance of let's do it even a little bit differently for all x. Do we want to do that like that or like that? No, not like that. There are two different notions that I'm thinking of, and I'm just deciding what I should take. Actually, yeah, I would like to take this. Oh, epsilon 0 for x 0 and r. . just before for epsilon bigger than 0, there exists a delta bigger than 0 such that when the distance don't care about this funny signs if you never saw them funny uh, nomenclature or funny notation. It's just we'll discuss all that in order. It's just to demonstrate that the quantifiers can give you a headache if you are not used to them sufficiently well, right? And here, by the way, an important thing is, well, you see if you have all the two quantifiers like that, if you want to assert the truth of such a statement, and that just means you have to fix that, and you have to go through each one separately by fixing this. It's similar like by the truth values, like we filled them in, but here the set could be very large, right? So we fix one, and we go through all of them, and then we look at what it stays after that, and we have to establish the truth. What do we have to do to establish the truth, right? And then we went through all of this for this one, and then we switch to the next one, and we have to go through all of this again, and so on. And if we have established that, so it's kind of establishing it for pairs, right? For all possible pairs like that. The kind of Cartesian product, yeah, because the order doesn't matter, so we could assign first order to this, okay? I mean, the order not of the quantifiers doesn't matter, but the order doesn't matter in our okay, let's say the order matters because the order of the quantifiers matters. That more intuitive. What I wanted to say, well, doesn't matter. I just mean we could have taken such pairs. But of course, because we quantifiers, of course, the order here doesn't matter because going through all of this and going through all of this for each of this, or going through all of this and going through each of this, that would have gone through same things. It would have checked these conditions that came afterwards for same things. But since we said the order paired are not equal, of course they are not equal. But on the level of interpretation, of what is happening here, it is also important. The context is important. Going through all of them would be same as going through all of them. So we could have switched quantifiers, would be same action. But if we interpret it in terms of ordered pairs, of course it is not the same. So more appropriate would be saying we go through all such. But okay, those details for now don't matter. We will uncover them subsequently. Of course, not necessarily explicitly, but you will just see how it works. We internalize them like in a self-explanatory manner. Okay, well, let's just look at some things, right? Let's write here is a number and just in the initial language and in the natural numbers such that n okay such that n is not the smallest number and there is, you should keep it in mind, it always means there is at least one. I did not even state that because I forgot that it is not self-explanatory, but it means there is at least one. It doesn't mean there is only one. By the way, notation, there is only one. Definition, notation. denotes there is exactly one, and we don't talk about only, we talk about exactly one. So not in the everyday language, but in mathematical language there is exactly one. For example, there is exactly one n element n such that for all m element n it should not be sloppy, such that for all m n is small or equal. Maybe you have to get used to it a little, think about it. It's just saying there is exactly one smallest natural number, which is obvious. This number is just 0, and any other one is not the smallest, so there's one, right? But well, just think about it. How does that? With quantifiers, you just have to have a little practice. There's a number n, and again, such that n is not the smallest number, and not the smallest natural number, of course, but it's obvious. Right? I'm talking about this. N is not the smallest number, and is larger than any number divisible by 3 or 4 between. Okay, it's a lot of complicated stuff for nothing, but I'm just trying to show you something how quantifiers work, so to speak, between 1 and 5, and you know. Between 1 and 5 is larger than any number divided by 3 or 4 between 1 and 5, and you see that some things are redundant. It is of course not a small number, it is larger. Yeah, it doesn't matter, it's just an example. We could write it mathematically, and n is more than 6. So if you write that in quantifiers, we could write it in quantifiers in different ways, of course, but I'll take a especially nasty one. There is a natural number such that for all m, and I'm just trying to get you used to that, right? For all m, and n, well, okay, not that nasty. There's such that I could complicate it even more, but I won't do that. I won't think about how to do that. So let's keep that straightforward. There exists m element n that is small, that is just a set of natural numbers small or equal n. And if it is not the smallest, that would not say that it is not the smallest, because that would be just, that would include just number n. Right, because n is small or equal n, namely n equal n, so in particular small or equal n, such that n is not the smallest number, n is larger than any number that is we have that. We have and. And there is no number. No, let's call it an okay. Okay. And if I write a comma, I mean both properties, or maybe even more than two properties. There exists no k, and simultaneously there exists no k such that and that is large or equal, and there exists no such k that is between that and this large or equal. It's just a fancy way to write, fancy and redundant way probably, that that is larger than any number. Of course, you don't have to write like that, but well, I could. There's no k such that it satisfies these conditions, and k is big or equal. These all k's are smaller than n, so that is larger than any number. By 3 or 4. That's already it. Yeah, that's it. Okay. Yeah, so you see, quantifiers allowed to write such monsters in a rather neat way, but of course that could have been written even easier. Here is and the smallest number. Of course, we could have written that explicitly, but there's no need. It's clear what we mean. So we can kind of use mathematical notation and nature notation once when it is clear, when it is exact and clear. And of course, larger than any number just means for k satisfying first conditions. So you have that, you have that, and you have that, and it's bigger. Okay, that same statement. And of course, might be wrong, might be true, but of course it is true. It's just not the smallest number in here, and it is larger than any such k. Oh yes, there's such number, and you see it already from here. So there's a lot of redundant information, but I just wanted to show you the technical side, how you apply it, kind of. Right, but this is of course not that interesting. Yes, now get to the things where it really is getting applied, right? And that would be, well, that's 3.1 basics of quantifiers. And now get to the meat. 3.2 quantifiers sets and set notation. Of course, if we now can state mathematical statements involving quantifiers, we can also define sets that are defined by some rules that are constituted by statements that involve quantifiers. Right. Now you'll be faced with the first thing which we want properly introduced because it's just, well, it can be properly introduced with definition or notation. It can be properly introduced in abstract set theory, and I mean like set theory that is real, but we won't do that, of course. It's just because for all purposes of dealing with that, it just suffices to think of that as it is introduced. There's no need for that, and it's really a simple thing, but yeah, there are hidden things behind that, but okay, we do not care about that much. Okay, definition, notation, index set, and indexed set collection sequence. Doesn't matter how you think about it. Let I be a set, and I mean any set. It could be, for example, R, or it could be R squared, where R squared denotes, of course, the Cartesian product of R with R, or it could be R Cartesian product R, Cartesian product R, Cartesian product R, Cartesian product R, or it could be R Cartesian product R, I don't know, like 100 times or something. Right. Let I be set. Then define I element I sets whose number, and of course we don't mean number exactly, because for example number of real numbers, if that would be the set R, right, that's just infinite, and number of elements in n, if we would take n, would be infinite, but whose number is equal to number of elements of I accounting for possible repetitions. That is, we are allowed to repeat same set, and it would not be counted just once, it would be counted all the times that when it is repeated, right? That is number of elements, not actually in the set, but in the I tilde J, and we just go for all of that. And this is just a collection of sets. And the number, and you see, mi could be equal to mi tilde, and so on. There could be a arbitrary number of repetitions, but since we now took an ordered tuple, that wouldn't be pair, of course, but if we would take only two, it would be a pair, right? And in the pair, it is allowed that the elements are the same, right? So here it is kind of an extension of an ordered pair. And don't be confused, there's nothing abstract going on, it's just introduced like that, that's it. And well, this is just some sets which have same number. What does it mean? Well, that just means that I for each set has exactly the indices, and so it goes on, and it like assigns, it can count, so to speak, it can go through the all sets in here by its elements, and that's just that. And just that, you don't have to think about it a lot. There's nothing deep behind it. It's exactly that. With I, with elements of I, we can go through all such sets. And those sets are called index sets. And that are indexed. Indexed by I. We really mean just indexed by I. Example. And we take just simple examples. Right. Example. I equal. Let's go with I1 because it's first example for that. I1 is equal to 1, 1, 10, and m I element I1 is an equal, and we just take the sets somehow, right? The important thing is just we can go through all of them and give them indices by just going through I1, right? That's just that. There's really nothing deep behind it. Oh, let's say we take something more interesting. I.II is video numbers, and I element I.II is equal to, oh, I.II is real numbers, right? And we could just say 2R, right? That's a set, and we can index it by R2, And index, it really means just its same, in a sense, number, right? And then I write R instead of R2 because it's the same thing. It just is R, it is chosen as R, so I can have that family of sets, right? So yeah. Set collection sequence family. Also use the notation. Also use the term family, and we use interchangeably the notation like that and like that because it's really like it's important what we mean by that and not really what we do with that, because what we do with that is really already determined by our meaning that we can go through them. That's all the things we want. We don't want anything else. So I mean, we don't want anything more. It suffices to just be able to go through it. Okay. Oh, now something interesting comes. Definition. And from now on, I won't state the index set as a separate object. It just belongs to a family, so to speak. Definition M1, Mi, a family, and then of course an index family. And that just means let that be an index family. Then we define the union over the whole family. No worries, it is a definition. It's just a definition. But how is that defined? Well, it is defined in a very self-suggestive way. That is exactly mathematical objects X such that there exists an I such that X is an MI. And of course, you could also like informally write, no one does that, but it's just what it really means. What that means that here exists, well, what it means. And you remember that is at least one, there is not only one, there is at least one, only one would be that, right? Written here additionally, an exclamation mark, and that just means really X and I, or X and my children, or and those go through all MIs, and that is all MIs for I in I, right? But it's not written like that. The formal thing is that, because this is formally clean, right? This is mathematically clean. But what is meant is actually that, yeah. But what is meant formally is that, and you should learn to understand it in that fashion, that it really works. Okay. And define this. This is just union over the family. You could call it over the family. Maybe there are also different names for it. I'm not sure, that's why I'm not writing it down, but well, you just have to name it somehow. And of course, what could be here, and you know how you can write it in the natural way. Well, kind of, because you actually cannot write it like that, but kinda. And the index set is not specified, it's just about existence. That is why the quantifiers are very useful, right? Or when the set is too large, you just can't write that. But this means exactly that, right? But here, of course, just for I in the family, you have that X is MI. And that's it. Okay. And now Let's call it theorem even. Theorem De Morgan laws. For any union intersection. Well, we will state them only in terms of complement, but of course it works generally. But it's just what we'll need, right? And we need a superset first. Let X be some superset. So if we use that notation, then clearly it is about sets. Let that be some index family. And if I use that, I just mean, well, for I and I, AI, a subset of X, but that's self-suggestive, right? Well, not necessarily. You could think that's really a subset of that, like as a set that is a subset of that, and that really contains like all the sets and things like that. But no, I just mean that. For each element of that sequence of sets, AI is really a subset of X, nothing else. So another level of structure, the lower one. I didn't understand why I clarified that. Just forget it, never mind. Let X then have, and now we have the Morgan laws, no generality, or no generality, but stated only for the complement. Right, then have first the definition we just stated, just here. And we take the complement, and here, as I said, when we know complement with respect to what, then we omit this X index. Of course, it is here complement with respect to X. What could it be else? Right, and we just have to put it, oh, that is what we claim. We don't know it, just have to put it here. And pay attention, for infinite index sets, we can't just use our simple De Morgan laws, because we don't have a proper way for translating just a finite number of those De Morgan relationships into arbitrary number, not just infinite, but arbitrarily infinite. Because they are different infinities, but no more on that for now. And this is, I really mean that. It is not written like that, but you understand that I mean that. And usually it's written without those parentheses, but okay, let's leave it. Okay, so, and that proof I will really do, because like it's some heap of abstract notations, so let's do that. But of course I will cheat a little bit, cheat in the mathematical sense, but it will just maybe drive you crazy in sense how abstract it gets, but well, not cheat in the sense that it will be somehow unclean. No, of course not. That's not what I mean. Okay, proof. Well, when you do such very abstract proofs, you have to stick to the definitions first. Within your mathematical development, at some point, you will understand that it's not that rigid of a requirement, and that you can think in other ways that kind of raise your thinking to the higher level than level of definitions. But okay, nothing concrete anymore for now. We have to stick to the definitions, and that is how we have to think, because we just have to learn that very simple steps of thinking. Those very simple steps of thinking. All right, there exists and I and I such that X is an I. Right. And we have complement of that. I have just written this set by definition, and since it's exactly this set, complement of that is of course equal complement of that, because I just took same set and applied to a complement, so of course it's this equal. Right, so equality here is clear. Right, now complement, what does complement mean? Well, that just means that I take X, our set of which those were subset, without this. Right? That's just definitions. All right, if we write that in the language of a set, what do we get? Well, it's X. Okay, that's a little bit, that I took big X here. Okay, don't be confused. X is just some mathematical objects. That big X is our superset. Doesn't matter. So this is kind of more general thing. Okay. Of course, it's a little bit confusing, but yeah, doesn't matter actually. So, and you recall the set theoretic difference and not, so we negate that statement. Here you can note it as a rule, or you can think about why it is logically valid. Actually, we would have to state it as an axiom because we have defined it as an abstract way. When we have such a negation, then all the quantifiers turn, and I mean all the quantifiers, turn into the other quantifiers. So such quantifier would turn into for all would turn, so all subsequent quantifiers will turn around. Like if you have something like that, ta ta ta, ta ta ta, ta, and you can think about why it's valid, or you could regard it as axiom. And then you have first that. What is that? That's not necessarily same, but let's just think about it for a little while. But we quantifies turn. That is that what you already know. Okay, we quantifies turn into the other quantifier. And we have only two types, so of course we also have unique existence, but okay, let's not think about it. We don't have it here. All right. And let's just think logically. If that statement is not the negation of this statement, I mean, this statement is not, what does it mean? Well, that stated there exists an I such that X is in AI. That is, the negation of that would be that there exists no. So the very simple negation would be just to do that, right? But in mathematical terms, if we wanted to like write it properly so that we have the quantifiers in it that allow us to apply subsequent definitions, so to work with it, to bring it forward in order to actually in the way so that we actually achieve what we'd like to achieve, right? And we'd like to achieve that thing, right? So in order to bring us forward, we'd like to rewrite it differently. And now let's think about it. Well, there exists an I, element I, such that X is in AI, right? So at least one there exists, all right? And we want the opposite of the statement. Second layer of interpretation, opposite of the statement. What does it mean? Well, if we want to formulate it in terms that bring us further towards the thing we'd like to achieve, then that would be something like that. We quantify terms for all I element I. It is true that x is not in there. So for all I element I, the opposite is true, which is exactly equivalent to this is not true. So for all I element I, this is not true. So the existence turns into for all, but for all for the opposite statement. So what we actually do, we turn all quantifier, leave those statements be, so that is same statements as here, but the last statement is turned into the opposite. But this is now informal, just think about it, okay? And I think the best way is always to think about it, but okay, if there are like 4 quantifiers or something, well, then it's sometimes better to just turn and look what happens and to look that, well, it makes sense. Right, and this is our end, right? So, note of this statement is for all I in I, that is not true that this is the case. And that is equivalent, of course, if you think about it, that is equivalent to not being able to find such an I within all I in the set big I, such that this is true. So this is indeed same statement as not this statement. Right, of course, maybe you have to think about it. I have to think a little about it myself because I like to see things like immediately. In this case, it's just how it works. So I mean, it's not immediately intuitive. It's intuitive on the level of mathematical thinking, but it's not immediately intuitive in the everyday thinking, right? So not there exists an I such that x is in AI, and we take not, and that is same as for all I element I. X is indeed not in AI. Right. And now we continue. Well, we just see what that is by definition. We actually are already done. We actually are already done because we just apply the definition. All right. No. We are not quite done. We are not quite done. Because we would actually like to put that inside to use the definition of our x without AI, right? So how do we do that? Well, we just think about what it is, or you could regard it as axiom. And no, I'm not stating that any inconvenient thing is axiom. It's just how it works. It is just how it works in mathematical logic. Just gives that. I mean, not mathematical logic that is stated in clear terms, but here you like mathematical logic explicit on the second layer of interpretation. Because you see, quantifiers in general, so the things that deal with too many objects at once, so to speak, they are not apt to elementary discussion. So you can't really say what are the elementary rules with them. You could state those rules as axioms, but that's it. You can't just say, well, that is because of that and that. No, you can't do that. You really have to rely on your exact mathematical intuition, but it's really that. So at some points or at some places in mathematics, it's just how it is done. So that this is actually allowed to be reformulated as this. This is just, you see that, and this is not justified by any laws or axioms unless you state this as axiom that you can do that. But well, let's look at this and see that it is pretty self-suggestive. It's just that here you have that this is true and this is true. And of course, you could have done an additional step. You just have that, if you just have this statement, right? So you kind of have, of course, it's like, no one does that, but let's do that. Well, you could have done that, right? If x is already element x, then it is independent of I. And this is kind of tricks that are done, not in this context it is done in mathematics, but this is done in mathematics. In certain other contexts, and in those contexts is considered to be like a proper way. But actually what is done here is exactly that. Since x is independent of y, we could just write for all I element I, x element x. It's a valid thing because here it is just stated x element x, right? And stated not in sense of truth, but stated in sense of the definition of the element of this set, right? But we could state that because if it is just stated as this statement is certainly equivalent to this because I just doesn't enter here. So of course it is valid for any I that we take because I is in parallel to this. It just does not influence anything of this. So the truth of this is independent of this truth. And so of course it is valid for I. And then you see that if you take any I and you take any I in here, then you have simultaneous validity of this statement for this I, and you have validity of this statement for this I. So you could kind of conflate those two quantifiers, and you could conflate that via and kind of like taking this out of this bracket with quantifier. So this is not how it is usually shown. This is just taken for granted that it works, but this would be the proper justification for that. Or you could just say an axiom. You could say that is an axiom. We can take out the quantifier, or you could say that is already the axiom. We can interchange that as you like. It's just how it works. And you just see that in all situations, it just works like that. And it works like that consistently in the general meaning of how mathematics works. But this is all I can give you. So at some points you have just to see what makes sense and you have to go by it. You have no way. And now here you recognize what this describes, what this x describes, right? This actually describes this set x without ai. And what it means that it is described, they see that within the description of the set, you can think about it if you would like. And now see that, and that is just that. So you see there was, if we look at that very closely, some hand waving, but that hand waving was exactly logically justified, exactly in total accord with any intuition that would have dealt with that. And of course, as I said, in a very abstract setting, no one does that, but in a very abstract setting, you could just state all that axiomatically and that would be completely valid. So the thing is, in mathematics, you go at some points exactly by your logic. If the logic exactly coincides in its consequences and its way with what are actually the established truths or the established definitions, all right? But what distinguishes mathematics from other disciplines in that point is you should go by your logic in that way that there is the way to state proper axioms with sufficiently low informational density, that is, with sufficiently low informational input. So it should be simple axioms and just a little set of axioms, so that all the steps that you make result completely from those axioms. So kind of are derivable from these axioms by, again, a set of rules of concluding of sufficiently low informational density. But this is just, you don't need to know that. I'm just giving you an outlook of how you can think of those things where we were kind of unclean. And no mathematician, no professor would tell you, would agree with you that we were unclean, but we were unclean if you look at it closely. It's just that it's how it is done. It's how it is done, and that's why no one thinks of it anymore. But you could think of that. But it is a could. It is not necessarily a should. I do think of that, and I recommend you to think of that, because that way you discover pretty interesting things that you also use to derive your own ideas. Okay, but you could also get caught up in that pretty easily, as you probably seen my videos. Also in a way that it hinders you, but yeah, it's just how it goes. But it is exciting. It is certainly exciting to think about such things, right? On that, you have to agree with me, I think. Okay, I mean, of those things that are actually not included in the standard consideration. Actually, I have forgotten the last line of that. But you see, that is just the definition. And recall that complement was an X, so we have proved what we wanted to prove. Right, we have proved that. And this is indeed the Morgan laws as we'd like here, right. And now that was the proof of one. And now do the proof of two. Oh, I won't say it is homework, but well, I will do some nasty stuff. That is the proof going on, right, of one, of two. I will do some nasty stuff that you have already seen, but maybe it will drive you crazy in that context. Well, sorry, but I don't care. You could write it properly out like here. I won't do that. I will just use what we have established to conclude that this is indeed nothing else but, well, if you just think of that as, but okay, I will write some things out of how I come up with that. Complement of the complement, it's just the set itself. Right? I just replaced each AI by complement of the complement, and you can see very easily that that is X, that is some AI. And if I take complement of AI, then I'm here. And now I take complement of the complement. So I take the set that complements the complements of AI, and I switched by taking complement of AI to this set. And now I switch to the other set, so it's AI itself. But you would prove it, of course, rigorously, if you like, that this is true by the shaking both of the Subset relations could do that, of course. No one is hindering you from doing that. Okay, now I use this nested fake. I just use one, like, right, we established one, so I can use that. And I'm using it now for complements, right? I'm using that for the sets, and I took complements here, and I consider those sets as my new AIs, and I use one. So I'm arriving at this here. And pay attention, this complement is here, but this complement, the again are eliminated because that is a set, that is complement of the set, and that is complement of the set. So that's exactly that. And pay attention here, I just used one using it on the sets AI complement, right? That's exactly that, and I used kind of it in reverse, but of course equality is asymmetric. That's that trivial of that, I'm not staying it. So here I complement, and here I go to there, and you see here I would have just complements here, and I would have complement of that, which is exactly that here. Like that comes from one, and that complement was already there. So yeah, let us complement, and with that the proof is finished. Right, so we had already some abstract stuff, and we have discussed it pretty thoroughly, at least here. And here you have just some challenge to think about. You could also establish that in that way also. Maybe do that, I don't know. But you could also think of that and how it works and how what structures are involved in what relationships and how something works and where these sets are chosen arbitrarily and hence allow application of some purely structured relationships. You could think of all that. I would recommend to think of all that. But okay, I think we are finished with 3. And next up we have maps. Right. Next up for the maps. Well, and I'd like to finish at this note. All right. I hope you are managing there.